Good afternoon, everyone. Welcome to 13th class of stochastic control and communication. So let's do a recap of what we were doing in this class. So we saw dynamic programming where history-related policies. Till now, we were looking at till now we were looking at Markov deterministic policies, but while we were trying to find optimal policy using dynamic programming. So we saw some examples of these. We saw inventory control. We saw the secretary problem. We saw a linear quadratic regulator. But our main point was there are other types of policies also, right? So the other types of policies that we didn't look into was Markov random policy, randomized, history dependent, deterministic policies, and history dependent randomized policies, right? So what we want to show is the optimal cost under HR policy, that is history dependent randomized policy, is equal to optimal cost under Markov deterministic policy. Right? This is what we want to show. Okay. This is our main goal. So if I know this, then I don't need to search under all the history dependent randomized policy. It is just sufficient to search under all the Markov deterministic policies. Right? So to do that, first let us come up with a formal definition of uh, the principle of optimality and dynamic programming algo for HR policy. We need these. Okay. So before diving into these two, let's refresh our knowledge on history dependent policies. So history dependent policies, basically you have 5HD, which is a set of history dependent deterministic policy. Okay. So if you have a policy which belongs to the set of history dependent deterministic policy, then basically I'm giving a vector of strategies. So this vector, each of them is a decision rule or strategy. Okay. And what do I mean by strategy here is, so this is a function. So mu t, a function which takes a history and maps to an action. So this is your history space, and this is your action space, right? Where if you have a history belonging to the history space, that means you have a vector of all the information till then. So you have a vector of state 0, A0, state 1, A1, and so on. State T minus 1, AT minus 1, and ST, the current state. You don't have the information of AT. That we will get if you give this vector to this function AT. You'll get the action that you need to choose, that is AT, right? So what you get is if you input this vector into the argument of AT, so S0, A0, S1, A1, ST minus 1, AT minus 1, ST. This is AT. This belongs to your action space, right? So this is your set of history-dependent deterministic policies. This is how you define the set of history-dependent deterministic policies. Suppose you had the set of history-dependent randomized policies. So phi HR, your set of history-dependent randomized policy. So if you have a phi which belongs to phi of HR, that means again similar to the above thing, you have pi 0 to a vector of functions. But here these functions, because of this randomized policy, you have phi t maps from ht to a distribution over the set A. This is your set of distribution, set of probability distribution over the action space, right? So now what you have is you have mu t is equal to mu t of S0 A0, S1 A1, so on, ST minus 1, AT minus 1, ST. This is basically Q mu t ht and the action, like some action, this action belongs to A T, and then you get a probability distribution. So this is basically the probability distribution over the action. So we have Q mu t ht. This is greater than 0 for all A belongs AST, and summation over A belongs to AST is Q mu t ht. Overall A, it is 1. So basically these two definition gives you that this is a probability distribution. over actions that belongs to the set A. Okay, next we saw the rewards. So for the rewards, you have RT, ST, UT, HT. Right? If UT, HT, or if phi belongs to set of history-dependent deterministic policy, then your reward RTST mu THT is basically it. Yes, also is basically RTST 80, right? Where this is your history, and this action is basically your mu THT, which is 80, right? From the definition of history dependent deterministic policies. Okay. But if your actions belongs to pi of HR, randomized history dependent policies, then you have RT, ST, mu T, HT equal to summation of A belongs AST, RT, STA into QA, mu T, HT. So this is the probability that you choose action A if you have history HT. If this is given, right, that is probability that you choose 80. And this is the reward you get if you choose action A at state ST, right? And ST belongs to the vector HT, right? Because it's the last element of HT is ST. So this is basically your average reward you get if you follow the randomized policy pi. Because your policy is random, so the actions that you choose will be random. So therefore, the reward of the work is expectation over the randomized policy or the actions. Okay. So next, if you want to write the total reward, total reward. So basically, you'll have expectation of RNSN plus summation t equal to 0 to n minus 1 RT comma UTHT. Okay, so J pi of S0 is basically expectation Rn Sn. This is your initial condition, initial state, initial starting state equal to 0 to n minus 1. But since you have here your pi belongs to history dependent randomized policies, right? So you will get summation A belongs to AST RT STA into QUT HT. So this is your total expected reward, where you have the terminal state reward and stage wise expected reward. So next we saw the transition probabilities. So similar transition probabilities, what you want to find is you want to find the probability that you'll end up at state J if you start at state S if you follow the policy using your pi belongs to history dependent randomized policy, right? This is basically summation over again all action space. You have a transition probability if you know what the action is, but this action is random. So you can the probability that you choose action A is basically this. So this is your transition policy, right? So this is the probability with which you choose action A, and this is the probability with which you transition to state J if you are at state S when you choose the action. So again, you're taking an expectation over all the randomized actions. So this basically tells you the probability that you reach state J when you start at state A, given you take the policy of the randomized policy. So this, just for a shorthand notation, we can denote this as probability pi J condition by S. Okay. So what do we want to find? We want to find the J star S0 optimal policy. So it's either max or min, depending on whether you're maximizing reward or minimizing cost. You want to find the policy over all history-dependent policies, history-dependent randomized policies, such that you maximize or minimize. So maximize the reward, right? So this gives you the total cost if you choose policy pi. And this is the optimal cost. Now, we had a similar form of formulation, but instead of pi HR, we were looking at pi MD, Markov deterministic policies. For that case, we formulated the method of we identified a property of the Markov deterministic policies, the principle of optimality, and we came up with an algorithm known as a dynamic programming algorithm. Now, what we want to do is we want to do a analogous case to the history-dependent randomized policy. And yes, the last class we saw that there is actually an analogous to the uh, to the history dependent random policy to the Markov deterministic random policy. But first we have to define the truncated problem, because principle of optimality use the notion of truncated problem. The truncated problem I define here as GT star HT is equal to max. So I'm maximizing over rewards, or you can minimize over cost. Pi belongs to pi HR J P pi HT, right? And where this is your reward, you will secure if you apply policy pi for the truncated problem. And this is your optimal reward. Right. It could be optimal reward, it could be optimal cost. So it could be maximum reward or minimum cost. So when I say it is the reward that you will apply for the truncated problem, what do I mean by the truncated problem is J pi of HT is equal to reward incurred or obtained from time t onwards till time n under policy pi belongs to pi HR, starting from history HT. So it's basically saying that you are at time t, and then you want to come up with an optimal policy for only the problem of solving till from t to n. Okay? So the principle of optimality says that if phi belongs to the set of history related randomized policy, history dependent randomized policy, where your pi is a vector of strategies. If this is optimal for the MDP, then pi t equal mu t to mu n minus 1. So this is the truncated problem. Is optimal, but max min. So that this is your truncated problem. Right? And this is, in short, your principle of optimality. But for uh, history dependent randomized policies, but for HR policies. Okay. So let me write down the Bellman equations for history dependent randomized policies. Okay. So first you start with Jn of Hn. This is the total history till time limit. That the reward is just dependent on the terminal state because the terminal. Okay. So this is your terminal condition. This you have to write it for all Hn. Okay. And next you do this for JTHT equal to max or min, depending on whether you are maximizing your reward and minimizing your cost. A belongs to AST, such that your one step reward plus HT plus 1. But this HT plus 1 here is just a vector of S0, A0, so on, ST minus 1, AT minus 1, ST, AT, and ST plus 1, right? So you can write this as HT, comma A, comma J, where HT is again a vector, right? So you will get X or min A belongs to AST, RT, ST, comma A plus summation of J belongs to S, P J condition ST, comma A into JT plus 1 HT A J. So these are your Bellman equations, and these are similar to what we had when we were searching over pi belongs to pi MD. But here the complexity is far here. The complexity is far more because you have to do this for all HT. And here you have to do it for all ST. So the cardinality of HT is way greater than cardinality of S. Right? So what we'll want to show is that this JTHT is not a function of HT, but a function of the current state ST. If we are able to show this, then we get the implication that the that optimal policy will depend on current state and not only the to, not the total history. If you are able to show this, we'll we'll show, then that implies our claim that the optimal cost from MD is equal to the optimal cost from HD HR. Right, so no need to randomize your policies and no need to depend on the total history. Just Markov and deterministic policy would be sufficient. Right, to show this, we'll define some terms first. So first is J star S0. Optimal reward or cost function for the MD. This is the optimal cost or reward for the MD. Okay, next you have J pi S0, which is cost or reward calculated under the policy pi. JT pi HT is basically the cost or reward to the truncated problem, that is from T to N. So you're solving the problem of finding the optimal cost from T to N under policy pi. So basically, this is the total policy. This is the truncated version. Truncated version. Okay. Next is JT star HT. Yes. Optimal. Okay. Here, this is optimal expected cost or reward. This is also expected cost or reward. This is also expected cost or reward. So optimal expected reward or cost of the truncated problem under I belongs to is history dependent randomized policies. Okay. And JTHT, this is the expected reward calculated by the Bellman equation. Okay. So in the same way that we tried to show in the Markov dependent policies that these two are equal, these two are equal. Same way here also we'll show that we'll assume basically because it's the same proof again, you have to again mathematically show by induction that JTHT equal to JT star HT, right? This will not show, but we'll just state the theorem. This we had shown this claim for the dynamic programming algo for the case of Markov deterministic policies. Right, but this is also true for the history dependent randomized policies. It is actually the same way you do it through induction, but then you have to just keep a note on how do you split this and then add this here and show that it is the outcome. Right, it's the same. It's the same. Okay, you show it by induction. So I'll just write down theorem. We'll not go into the proof today. So the theorem is, suppose JT for E equal to 0 to N, solve 1. Here 1 is these two equations. So this, so these two together is your 1. Solve 1. Then we have JT star HT equal to JT HT. For all HT belongs to history and T belongs to 0 to N. Okay, this is something that is easy to show and I'll not show it here. So we'll do the proof of the next theorem. This theorem is for each t belongs to 0 to n, jt star ht depends on ht only through st. This is the optimal reward or cost for the truncated problem, right? We have shown that this is equal to JTHT, that is given from the Bellman equation, right? We'll use this theorem to show this thing. We have to show that this is equal to JT star, just a function of ST and not the total HT. We have to show this. Okay. So oops. Okay. The proof is also by induction. So the first claim is JN HN equal to JN star HN equal to RS, right? This is from the previous theorem, and these both from the Bellman equation. Okay, therefore, this is the base case. The base case, we have shown that J star N HN is the function of SL. Next, we have the assumption case. So let us assume that claim is valid for t equal to k plus 1 to n. This is your hypothesis. This is your hypothesis. So it's valid for k plus 1, right? So jk star hk is equal to jk hk. This is from previous theorem. Okay. And this is equal to max or min, depending on whether you're maximizing the reward or minimizing the cost. A belongs to AST Rk sk comma a plus summation j belongs to S P j conditional sk comma a into jk plus 1 h k plus 1. Okay, but this hk plus 1 can be written as hk a comma j, right? So I write this as hk a comma j. But so but from the hypothesis, we know that jk plus a hk comma a comma j is just a function of j, right? So you can replace that here. So here you can see that now this is a function of xk, this is a function of xk, and this j will this is the next state, right? So you'll do it for all j's that goes to the next state. So here basically you have removed this step, you have removed the dependency on the history, right? So this whole thing is basically jk of s. Okay. And by induction, the result holds for all t equal to 0 to 1 to n. So it is done. And what we get from here is there is no benefit in the optimal cost slash reward in randomizing your policy. There is no benefit in the, these are your two observations. Optimal cost or reward in taking the look at a whole history dependence. So therefore, max pi belongs to pi Markov j pi s0 equals to max pi belongs to history dependent randomized j star s0. Optimal Markov policy is same as your Markov optimal policy. This is what your claim is. Okay. So basically, what we have shown today is that you don't need to look at the whole history to You want to look at the whole history to come up with the optimal policy, or if even if you look at the whole history to come up with the optimal policy, it is sufficient to look at Markov deterministic policies, right? Because the optimal policy you get there, it might not be the same policy, but what will happen is the optimal cost that you get from it is will be remain the same. You can do no better by looking at history dependent policies, right? So is this always the case, or is this because you have the perfect history, like the information that you get at each time, you exactly know what the state is, and because of this nature of information gathering, uh, these types of policies come up, right? But there are also a new class of policies known as imperfect information. So what happens if we do not have the exact state information, but some corrupted form of information? Then what do you do? And you'll see that in these types of problems, it is better to keep the whole history of observation. We will see this in the next class. I'll stop recording.